Have you ever looked up at the night sky and wondered about the stars? A sea of twinkling lights, each with its own story. Astronomers have a tool that helps them decode those stories. It's called the Hertzsprung-Russell Diagram, or HR diagram for short. Like a map of the cosmos, it charts the lives of stars. The HR diagram isn't just a pretty picture, it's a powerful tool. It helps us understand how stars are born, live, and eventually die. The HR diagram is like a snapshot of a bustling city. But instead of people, we're looking at stars. It captures stars at different stages of their lives, from their fiery births to their quiet fades. By plotting stars based on their brightness and temperature, we can group them together. These groups, like the citizens of our city, share common characteristics. They tell a story of stellar evolution. Section 2. Stellar fingerprints, luminosity and temperature. Every star has a unique fingerprint, a combination of luminosity and temperature that sets it apart. The HR diagram uses these two properties to create a visual map of the stellar population. Luminosity, or absolute brightness, tells us how much energy a star emits. Think of it as the wattage of a light bulb. The higher the wattage, the brighter the light. Temperature determines the color of a star. Cooler stars emit a reddish light, while hotter stars shine blue. On the HR diagram, temperature is plotted on the horizontal axis, with hotter stars on the left and cooler stars on the right. Luminosity, represented on the vertical axis, increases from bottom to top. Section 1. A stellar landscape navigating the HR diagram. Picture yourself standing on the edge of a vast, starlit plain. The Hertzsprung-Russell diagram is like a map of this celestial landscape. Instead of mountains and valleys, we have stars scattered across the chart, each representing a different stage in a star's life. Think of the HR diagram as a cosmic family portrait, with stars grouped according to their shared characteristics. Just as family members often bear a resemblance to one another, stars occupying similar regions on the diagram share common traits. As we explore this stellar landscape, we'll encounter familiar landmarks like the main sequence, where most stars, including our Sun, spend the majority of their lives. We'll also venture into the realm of giants and supergiants and white dwarfs, the faint remnants of stars like our Sun. Section 2. The luminosity axis, measuring stellar brilliance. One of the key features that define a star is its luminosity, a measure of its intrinsic brightness. This is how much energy a star emits per second, regardless of its distance from us. Think of it as the star's inherent wattage, like comparing a dim nightlight to a powerful searchlight. On the HR diagram, luminosity takes center stage, literally. It occupies the vertical axis, increasing from bottom to top. This means that stars plotted higher on the diagram are more luminous, shining with greater intensity. This difference in brightness is crucial for understanding a star's life cycle. More luminous stars tend to burn through their fuel faster, leading to shorter, more dramatic lives. Section 3. The temperature axis, from cool reds to blazing blues. If luminosity is the star's wattage, then temperature is its hue. Just as a heated piece of metal glows red before turning white hot, a star's temperature dictates its color. Cooler stars emit a reddish light, while hotter stars blaze with a bluish-white intensity. On the HR diagram, temperature reigns over the horizontal axis. Hotter stars claim their spot on the left side of the chart, while cooler stars gather towards the right. This arrangement reflects the inverse relationship between a star's temperature and its color. As we move from left to right on the diagram, we transition from the searing heat of blue giants to the cooler embrace of red dwarfs. Now let's talk about the stars you see every night. Most stars in our galaxy, including our Sun, belong to a special group on the HR diagram called the main sequence. Picture a diagonal band stretching across the chart, from the top left corner, where hot, luminous stars reside, to the bottom right, home to cool, faint stars. This is the main sequence, the stellar equivalent of a bustling city center. Imagine a crowded street filled with people of all ages and backgrounds, going about their daily lives. That's what the main sequence is like, a diverse but well-defined group of stars, each at a different point in its life cycle. Despite their differences, these stars share a common characteristic. They all fuse hydrogen into helium in their cores. This nuclear fusion, the process that powers the stars, determines their position on the main sequence. Hotter, more massive stars burn their fuel quickly, shining brightly but living shorter lives. Cooler, less massive stars, like our Sun, are more frugal with their fuel, resulting in longer, less dramatic lives. Stars don't just magically appear on the main sequence. They are born from collapsing clouds of gas and dust called nebulae. Imagine a giant cosmic nursery filled with these stellar embryos, each one a swirling mass of potential. As gravity pulls the gas and dust inward, the core of the protostar heats up. When the core reaches a scorching 10 million degrees Celsius, hydrogen atoms begin to fuse into helium, releasing a tremendous amount of energy in the process. This nuclear fusion marks the moment a star is truly born, igniting its stellar engine and propelling it onto the main sequence. The exact point where a star joins the main sequence depends on its mass. Section 3. Stellar Adolescence. Life on the main sequence. Once a star joins the main sequence, it enters a long, stable period of its life, much like a human's adolescence and adulthood. During this time, the star continues to fuse hydrogen into helium in its core, maintaining a delicate balance between gravity pulling inward and outward pressure from the nuclear reactions. This equilibrium is what keeps a main sequence star shining steadily for millions, even billions of years. Think of a spinning top, perfectly balanced as it whirls around. That's a main sequence star in a state of hydrostatic equilibrium. The outward push of nuclear fusion counteracts the inward pull of gravity, preventing the star from collapsing under its own weight. This delicate balance allows the star to live a long and productive life. But even during this stable period, stars are not static. Section 4. Leaving the nest. The end of main sequence life. The time a star spends on the main sequence, its stellar adolescence and adulthood, is but a fleeting moment in the grand scheme of cosmic time. Eventually, like all good things, life on the main sequence must come to an end. The star's hydrogen fuel, the source of its energy and stability, begins to run out. Imagine a car running out of gas. It sputters, loses power, and eventually comes to a halt. Similarly, as a star depletes its hydrogen fuel, its core contracts and heats up, while its outer layers expand and cool. The star swells in size, transforming from a main sequence star into a red giant or supergiant, depending on its mass. This transition marks a turning point in the star's life, a departure from the familiar comfort of the main sequence, and a plunge into the unknown realms of stellar evolution. Section 1. Giants arising, leaving the main sequence. We've explored the bustling metropolis of the main sequence, where stars spend their youth and middle age. Now let's venture into the suburbs, where stars in their twilight years reside, the realm of giants and supergiants. These stars, much larger and brighter than our Sun, represent a later stage of stellar evolution, a testament to the ongoing struggle between gravity and nuclear fusion. As stars like our Sun exhaust their hydrogen fuel, they begin to cool and expand, leaving the main sequence and embarking on a new chapter in their lives. Imagine a balloon slowly inflating, its surface stretching as it grows larger and larger. That's what happens to a star as it transitions into a giant. Its core contracts, becoming denser and hotter, while its outer layers puff outward, cooling and reddening. This transformation is a gradual process, taking millions of years to unfold. Section 2. Stellar Metamorphosis, the expansion of giants. As a star expands into a giant, its physical appearance undergoes a dramatic transformation. Its diameter can swell to hundreds of times its original size, engulfing any nearby planets in its fiery embrace. Imagine our sun ballooning outwards, its surface reaching beyond the orbit of Mars. That's the scale of expansion we're talking about, a cosmic spectacle that highlights the immense power of these stellar giants. This expansion is accompanied by a change in color. As the star's outer layers cool, its light shifts towards the redder end of the spectrum. This is why many giants appear reddish or orange in color, a visual cue to their advanced age and impending demise. But the expansion of a giant is not just a visual spectacle, it's a sign of significant internal changes. Section 3. Inside a giant's heart, new elements forged. Within the heart of a giant, a cosmic alchemy is at work. The intense pressure and temperature created by the contracting core act as a giant furnace, fusing atoms together to create heavier elements. This process, known as nucleosynthesis, is responsible for creating many of the elements we find on Earth and throughout the universe. Think of a blacksmith hammering away at a piece of metal, shaping it into something new and complex. That's what's happening inside a giant star, but on a much grander scale. Helium atoms are fused into carbon, carbon into oxygen, and so on, building up the elements that make up our world and our very bodies. Through powerful stellar winds and eventual stellar explosions, these elements are dispersed into the interstellar medium, enriching the cosmic soup from which new stars and planets will eventually form. Section 4. Supergiants, cosmic titans on the brink. While giants represent a significant departure from the main sequence, supergiants take stellar evolution to a whole new level. These cosmic titans, the largest and most luminous stars in the universe, occupy the upper right corner of the HR diagram, standing as beacons of power and impending doom. Imagine a star so large that if it were placed at the center of our solar system, its surface would extend beyond the orbit of Jupiter, engulfing all the inner planets, including Earth. That's the scale of a supergiant, a star that pushes the limits of stellar size and luminosity. Supergiants live fast and die young, burning through their fuel at an astonishing rate. The death throes of a supergiant are nothing short of spectacular, resulting in supernova explosions that can outshine entire galaxies. We've journeyed through the bustling heart of the main sequence and witnessed the grandeur of giants and supergiants. Now we arrive at a quieter corner of the HR diagram, a place where stars, having shed their outer layers, exist as compact remnants, the realm of white dwarfs. Imagine a star, once the size of our sun, compressed to the size of Earth. That's a white dwarf, an incredibly dense object, a testament to the relentless crush of gravity. Despite their small size, white dwarfs pack a punch, containing a mass comparable to the Sun. On the HR diagram, white dwarfs occupy a distinct region below and to the left of the main sequence. Though no longer powered by nuclear fusion, white dwarfs still radiate heat, glowing with a faint white-hot intensity. The transformation from a red giant to a white dwarf is a dramatic event in a star's life. Having exhausted its nuclear fuel, the giant's core collapses under its own weight, unable to withstand the relentless pull of gravity. This collapse releases a tremendous amount of energy, expelling the star's outer layers into space, creating a beautiful and intricate planetary nebula. Imagine a cosmic firework display, a dazzling spectacle of gas and dust illuminated by the dying star's radiation. That's what a planetary nebula is, a testament to the final act of a star like our Sun. At the center of this cosmic display lies the newly formed white dwarf, a stellar ember left behind after the fiery demise of its progenitor. This transition marks a profound change in the star's existence. No longer powered by nuclear fusion, the white dwarf is destined to slowly cool down over billions of years, eventually fading into obscurity as a black dwarf. Yet, even in their final act, white dwarfs play a crucial role in the cosmic ecosystem, their intense gravity influencing the evolution of companion stars in binary systems. A white dwarf, having shed its outer layers and contracted to an incredibly dense state, enters a long and uneventful retirement. With no nuclear fuel to burn, it's no longer a stage for the dramatic fusion reactions that power main sequence stars. Instead, it radiates its residual heat into space, slowly cooling down over eons. Imagine a hot ember pulled from a fire, gradually losing its glow as it radiates its heat into the surrounding air. That's the fate of a white dwarf, its once fiery heart slowly fading as it cools down over billions and trillions of years. This cooling process is incredibly slow due to the white dwarf's extreme density. The atoms within its core are packed so tightly together that they form a degenerate gas, a state of matter where quantum mechanical effects become significant. This degenerate gas resists further compression, providing a sort of pressure support that slows down the cooling process. Section 4. Exotic Encounters. White dwarfs in binary systems. Some white dwarfs in binary systems engage in a gravitational dance with companion stars. This dance can lead to dramatic outcomes, like novae or supernovae. Imagine figure skaters, one pulling material from the other. This material forms an accretion disk, leading to explosive consequences. These encounters highlight the enduring influence of white dwarfs. Just as the Rosetta Stone unlocked ancient Egyptian secrets, the Hertzsprung-Russell Diagram deciphers the star's language. By plotting stars' luminosity and temperature, it reveals stellar evolution, connecting brightness, temperature, and destiny. Before, astronomers had isolated clues. The HR diagram provided the missing link. Now we trace stars' life cycles, from fiery births to dramatic deaths. The HR diagram is a dynamic map revealing the evolutionary pathways of stars. It shows us where stars are headed based on their current position. Stars of different masses evolve at different rates, transitioning between stages of their lives. Their fates are determined by their initial mass. Our Sun will swell into a red giant, engulfing Earth, then become a white dwarf. Massive stars explode as supernovae, leaving neutron stars or black holes. They enrich the interstellar medium with heavy elements, seeding future generations of stars and planets. The HR diagram has not only revolutionized our understanding of individual stars, but has also provided insights into the evolution of galaxies and the universe as a whole. By studying the distribution of stars on the HR diagram for different star clusters, astronomers can determine the ages of these clusters, providing clues about the history and evolution of our Milky Way galaxy. Furthermore, the HR diagram has allowed astronomers to study stars in distant galaxies, providing a glimpse into the stellar populations and star formation histories of these far-off realms. By comparing the HR diagrams of different galaxies, we can learn about the similarities and differences in their stellar populations and gain a deeper understanding of the processes that drive galaxy formation and evolution. The HR diagram continues to be an essential tool for astronomers, guiding their research and leading to new discoveries about the cosmos. As we develop new telescopes and observing techniques, the HR diagram will continue to play a vital role in unraveling the mysteries of the universe. The Hertzsprung-Russell Diagram, with its elegant simplicity and profound implications, reminds us of our place in the grand tapestry of the cosmos. It shows us that our Sun, the star that gives life to our planet, is but one of billions of stars in our galaxy, each with its own story to tell. It highlights the interconnectedness of all things in the universe, from the smallest atoms to the largest stars. As we continue to explore the cosmos, the HR diagram will serve as a constant companion, guiding our understanding of the stars and their evolution. It reminds us that we are part of something much larger than ourselves, a cosmic web of energy and matter constantly evolving over billions of years. The next time you gaze up at the night sky, remember the HR diagram and the stories it tells. Stories of stellar birth, life and death. Stories that connect us to the vast and wondrous universe we call home.